All right, I'm going to get started going over some more examples of um, taking limits at infinity. Uh, Again, all these problems will be as x approaches infinity or negative infinity. Um, in both cases, it's usually about the same. Don't forget you have a test on Wednesday, or a quiz on Wednesday on 2.1 through 2.4. Today I'm going to finish these examples, then I'm going to go over some of the homework. Tomorrow I'll finish going over the homework and answer any questions that you might have. So, first, number 37. As I look at this one, I see it's 2 over x minus 3. Okay? So if I take the limit as x approaches infinity, of this whole thing, then that means that I'm going to take the limit and break it down into two pieces. Be the limit as x approaches infinity of 2 over x minus the limit as x approaches infinity of, of 3. So this is x approaches infinity of 3. Now, my limit as x approaches infinity of 2 over x. X keeps getting bigger and bigger. So this is going to go to 0. My limit is 0 for the first part. Then for the second part, there is no x in here, which tells us that the limit as x goes to infinity, this is a constant, it remains the same. 0 minus 3 is negative 3. That's my limit as x goes to infinity. Same thing with negative infinity. If all I'm doing is changing this to negative infinity, then whenever I change this to negative infinity, my limit's still going to be going 2 over negative infinity. So this is going to go to 0 because x is going to keep getting more and more negative. Think about 2 divided by negative 1,000, 2 divided by negative 7,000, 2 divided by negative 1,000,000. That's going to keep getting smaller and smaller, getting closer and closer to 0. So as that gets closer and closer to 0, it tells me that this part of our limit is going to get closer and closer to 0. So it becomes 0. The limit back here as x approaches negative infinity goes to 3. It's a constant function, so there is no x. There is nothing going to infinity, so it's just 3. It's still a minus, so this would be negative 3. So our answer for the limit as x approaches infinity is negative 3, and the answer for the limit as x approaches negative infinity is still negative 3. All right. For this next one, number 40, let's look at the limit as x approaches infinity. So again, I can break this up. Here I can take the limit as x approaches infinity of 1, which we all know at this point there's no x in this, so that's not going to change. I'm just going to get rid of that. Then we take the limit as x approaches infinity of 8 minus the limit as x approaches infinity of 5 over x squared. So if I break this down and do it a piece at a time now, the limit as x approaches infinity of 1 just stays 1, because there's no x in this part of the problem. Here, the limit as x approaches infinity of 8 is the same. It just stays 8. Back here, it's 5 over x squared. So again, think of x squared getting bigger and bigger and bigger and bigger to where we have 1,000,000 squared. That's going to make 5 divided by 1,000,000 squared is going to be an incredibly small decimal. So this just goes to 0. And it's that way anytime you have a number simply divided by an x. Any power of x is even smaller. So if this is x to the 5th power, that's even smaller than this is. Because if it's 5 over x to the 5th, that would be 1,000,000 to the 5th power. which makes my denominator so much bigger and makes this entire fraction so much smaller. So since this goes to 0, we just plug it in, and it's 1/8. Same thing for negative infinity. This x squared is just going to keep getting bigger and bigger negative, so that I'm still taking 5 divided by negative a million squared. Negative a million squared just turns into 1 million squared, because it's the same thing, so it would still give us 1/8. So those are some of the easier types. Now we scroll down to here. So this is where I have the rational functions start to come in, and it's the limit as x approaches, as 2x plus 3, as x approaches infinity, of 2x plus 3 over 5x plus 7. As I look at what this approaches, the first thing we want to do is divide by the highest power. So because these are the same exponents, I'm going to divide by x. So everything gets divided by x before I even start to find the limit. Because I'm dividing both the top and bottom by x, I'm allowed to do it. So 2x divided by x is just 2. 3 divided by x is 3 over x. 5x divided by x is 5. And 7 divided by x is 7 over x. Now I take my limit as x approaches infinity of all of this. From there I can break it up. It's the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x plus the limit, or over the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 7 over x. By now you should start to be catching on. If I'm looking at x approaching infinity, there's no x in this first portion. That's just a constant that stays 2. Limit as x approaches infinity, it's 3 over x. It's just a number divided by x. That's always going to go to 0 when x is going to infinity. Same thing down here. I have 5 plus 0. 7 over x, it's just a number over x that goes to 0. My final answer is just 2/5. If I went to negative infinity, it's going to be the same exact process. And I'm going to end up at 2/5. Questions? Now I have 2x cubed plus 7. Over x cubed minus x squared plus x plus 7. Again, they have the same exponent. And so we've covered these types before, if you'll remember correctly. That was when it's less. This is when it's the same degree. So this was our example in the notes. This is what you would come to if you were looking for an example. So, since these are both x to the third, I'm going to do the same thing I did in my last example. Limit as x approaches infinity. So I'm going to move this over because it's all so much longer. Now I divide everything by x to the third, or the highest exponent. So that just gives me 2 plus 7 over x to the third. And then x to the third divided by x to the third is 1. X squared over x to the third is 1 over x plus 1 over x squared plus 7 over x to the third. Now I take the limit of each part separate. Limit as x approaches infinity of 2. I'm not even going to rewrite this. I'm not even going to make you rewrite it, so I'm not going to rewrite it anymore. I'm taking the limit of each part separate as x approaches infinity. So the first part, limit as x approaches infinity of 2. There's no x in there. That's just 2. 7 over x cubed. X going to infinity. That's going to go to 0. Limit as x approaches infinity of 1. It's just 1. 1 over x is 0. 1 over x squared. Now if 1 over x is 0, then 1 over x squared has to be even smaller. This comes back to our sandwich theorem. So that would be 0. And 7 over x cubed, again, it's going to be getting even smaller. So that is also 0. My final answer is 2 over 1, which is just 2. So that's where we leave that one. Okay, I'm going to go over another homework assignment that we hadn't gone over yet. I don't think we went over it yet. Okay, so we're going to go over 2.3 definition of a limit day 4 homework. And let's start with number 34. So starting with number 34, we're using the formal definition to find this. So we're looking at the limit as x approaches negative 5. Because that's our x naught. And that's of this whole thing. Now, the first thing I'm going to do for number 34 is I need to figure out what my limit is. So it's the limit as x approaches negative 5 of, and I can first factor this top out, and that's going to factor out to x plus 5 times x plus 1 over x plus 5. Now my x plus 5s will cancel, and I'm left with the limit as x approaches negative 5 of x plus 1. Now I can plug a negative 5 in, and it's not going to do anything to mess this up. So negative 5 plus 1 gives us L equals negative 4. So now I'm just going to do my functional definition, which is going to go back to my original formula. Absolute value, x squared plus 6x plus 5 over x plus 5 minus a negative 4. Just plugging that negative 4 and the function in to our original, and that's got to be less than 0.05. Let's look at what our x minus x naught would be. Our x minus x naught is x minus negative 5, so that would be x plus 5. So that's kind of what I'm looking to get this equation to. So if I break this down, it's going to be the same thing that we just did. X plus 5, and I'm still leaving it in the absolute value for now. X plus 5 times X plus 1 over X plus 5. And then it's a plus 4 because it's minus a negative 4, 0.05. This cancels. I have X plus 1 plus 4. X plus 1 plus 4 is X plus 5. Absolute value less than 0.05. I can get rid of my absolute values now, and I get negative 0.05 less than X plus 5 is less than 0.05. Now if I look at this, then it automatically, actually I didn't even need to take that step if I really think about it. I'm trying to get X plus 5 because that's my definition for over here, this being less than delta and greater than 0, obviously. Since this is the same as this, I'm done. I have found my delta. So delta in this case equals 0.05. In other words, now my X would have to be between plugging in delta. Well, at this point, this is all we were really looking for. So I can stop because it doesn't ask me to find the interval. So we can just leave it as 0.05. If not, I could plug in an X to make it under between 0.05 and 0.05. But that would actually just be solving this out like I started to do, where it was negative 0.05 less than X plus 5 less than 0.05, and subtracting the 5 give you negative 5.05 and negative 4.95, and that would tell you your interval that X has to fall within. But just saying delta being 0.05 is good enough. All right. Next one, number 37. So here we had to kind of going through the same step, but not with an actual epsilon. So we're taking the limit as x approaches 4 of 9 minus x, and we're trying to prove that that's equal to 5. So I'm just doing absolute value of my function, which is 9 minus x, and then minus my limit, which is 5, and that's less than epsilon. And I'm looking for my limit as x approaches 4. So that would be x minus 4, with my x not being 4. So now we're just going to solve this for x. 9 minus 5 gives us x plus 4, negative x plus 4, less than epsilon. Get rid of our absolute values. It's negative epsilon less than negative x plus 4, less than epsilon. Subtract the 4 to each side. That's negative epsilon minus 4, less than negative x, less than epsilon minus 4. Now I have to get rid of my negative, which means that I'm going to flip my signs over here to be positive epsilon plus 4. And you have to flip the direction of your inequality now. Greater than x, greater than negative epsilon plus 4. And so just to kind of finish this off here, we're going to have 4 minus epsilon, keeping our inequalities flowing the proper way, and then 4 plus epsilon. All I did was switch the direction of my inequalities and flip this side over to this one. So x has to be between these two values. And now I'm solving my delta, with this being less than delta. And so it's x minus 4 less than delta and greater than negative delta. Then just solving this out, adding 4 to each side, that's going to be 4 minus delta is less than x, and 4 plus delta. And now whenever I look at this, the only thing that's different between this and this is I have an epsilon instead of a delta, which tells us that epsilon and delta are the same thing. So you would choose delta equal to epsilon. All right, well, that's as far as we can go today, because class is over officially. We will finish going over this homework assignment tomorrow, and we'll do the homework assignment that was due last week, starting this section, and maybe get into some of tonight's assignment. If you have any questions about any other section, you can ask those if we have time tomorrow, and just have a good day.